Okay, let's consider this question carefully as an example of needing to use the icebox to calculate KEQ. We're told that at 458 degrees Celsius, there was initially 0.8 moles per litre. That's all it says, full stop. At equilibrium, there was 0.0884 moles per litre of hydrogen present. Find KEQ. So like many problems in chemistry, part of this question is understanding what it's talking about. We're given here the chemical decomposition of hydrogen iodide gas. That should have brackets around it. So we've got 2 moles of hydrogen iodide gas will decompose into hydrogen gas and iodine gas. First thing I'm noticing is that my states are all gaseous, so it would all go in the K expression. Second thing, of course, is that I'm at equilibrium, or at least this is an equilibrium system, meaning if I start with hydrogen iodide, it can decompose to hydrogen and iodine, and at the same time, hydrogen and iodine will recombine to form hydrogen iodide. It's an equilibrium system. But the key is, once I've constructed the K expression, I need to know the concentrations of all 3 species at equilibrium. So let's go ahead and construct our KEQ expression. We now know how to say that KEQ will be equal to the concentration of the products, hydrogen gas, raised to their coefficients, of which we have none this time, divided by the concentration of the reactants raised to their coefficient. Hydrogen iodide, there's 2 moles of that, so I raise it to the power of 2. That's my K expression. But here's the key. I must put the molarities of each species at equilibrium in these brackets. I can't just put any random concentration that I'm told. I need to know what their concentration is at equilibrium in order to calculate K. So in the question, I'm told something interesting. There was initially 0.8 moles per litre. That means I started out with only this, and the reaction was allowed to proceed. So if we had a reaction profile or a graph of it where we had time on the x-axis and concentration on the y-axis, we would say that initially I had some hydrogen iodide, and over time that's going to decompose as the reaction moves forward. Then I start to form some of the product, and they can combine with collision theory and start moving backwards. So initially at time 0, I had none of these products. So I would have them down here at 0, and they slowly climb, and because it's 1 to 1, I'll just draw it underneath, but it would be the same trajectory like this. Now, that means that initially I have all of this and none of these. But it goes on to say, and it will always give you one more piece of information in a question, otherwise we couldn't do it, at equilibrium. So once these are flatlined and I've achieved equilibrium, say sometime here, at equilibrium, we're told there was this much concentration, this molarity of hydrogen iodide, of hydrogen. So I know how much of this one I have at equilibrium. And our job is to work out, well, therefore, how much of this one would I have at equilibrium and how much of this one would I have at equilibrium? At the moment, I know what I had to start with. I know what this is at equilibrium, and I've made no comment about this one. In order to do this, we need to construct the ice box. I for initial, C for change, E for equilibrium concentration. I then construct across the top each of the species present in my system. So here's my ice box. I have hydrogen iodide as a species, there at the top. I have hydrogen as a species, and I have iodine as a species. And I ask myself the question, what was the initial concentration of each of those species? Hydrogen iodide, I'm told, is 0.8 moles per litre initially. Of course, from my graph, I can see that I've got no product of hydrogen. So initially that was at 0. And of course, that means iodine was also at 0. Now, how has it changed? C is for change in concentration. Well, let's have a look at the data in the question. At equilibrium, there was now this concentration of hydrogen. So hydrogen has gone up from 0, and it's changed by 0.0884. Now you've got to use your year 11 chemistry. If I produced 1 mole of hydrogen, I'd produce 1 mole of iodine. If I had produced 2, I would produce 2. If I had 10, I would have 10. It's a 1-to-1 ratio. So obviously, if I now have this many moles per litre of hydrogen, I will have the same number of moles of iodine, and I showed that in the graph too. So I'm able to confidently now put 0.0884 in for iodine as well. Now this is the one that sometimes will trick chemistry kids up. Let's think about it logically. I've just said if I produced 1, I would produce 1. If I produced 2, I would produce 2. Now I need to have a look at my reactant molecule. See, if I produced 1 hydrogen, I must have used 2 hydrogen iodides. If I produce 10, I must have used 20. My ratios are fixed, it's 2-to-1. So if at equilibrium, I have now got this many moles per litre of hydrogen, that means that twice as much, 2-to-1, of hydrogen iodide must have decomposed in order for that to happen. In other words, the amount of hydrogen iodide that was used will always be twice as much as the hydrogen that was produced. So as a 2-to-1 ratio, I've got to double the amount of 0.0884 to demonstrate how much hydrogen iodide has been lost. So we need to put that into our calculator, which I've just got sitting over here. All right, so I'm going to put that in. 0.0884 times 2 is how much hydrogen iodide was lost, 0.1768. So I've changed by a fall of 0.1768. I'm just going to struggle to fit that in the box, I'm sorry, 68, a bit messy. Yours will be much neater, 10. That says 0.1768. I'll just write it here so you can see. 768, apologies. Now, if I initially had these amounts, I've changed by these amounts, I can now put in what my concentration is at equilibrium, which of course is what I'm chasing to insert into the K expression. I had 0, I've now got this much, so at equilibrium, I've got this amount, 0.884 moles per litre, of course, I'm just not putting the units in. This one's what the question told us I had, so I can put that straight in. I know that it's the same, 884. The question now is, if I start with 0.8 and I use 0.1768, I can do a simple subtraction to work out what I had. So 0.8, which is what I started with, take away 0.1768, which is what was consumed. At equilibrium, this is the figure I'm chasing, 0.6232. 0.6232. That's the molarity of the last species at equilibrium. This is the critical line. Now I can insert into my K expression. K can be found by... Okay, that was just all getting a bit messy, so I've just started a new sheet so that we get it right. So our K expression is going to be in reference to our icebox. So I've got it here just on my screen there. So I need the K expression again to be written. Let's make sure I've got that. I've got the concentration of hydrogen is going to be multiplied against the concentration of iodine, and I'm going to put that over the concentration of hydrogen iodide. These are all at equilibrium, what we've been working towards. Excuse me, that's awkward. Squared, I've got to square that because there's 2 of them. And then I simply plug it in. So K is going to be equal to the concentration of hydrogen at equilibrium, which is 0.0884. 0.0884. And I'm going to times that by the concentration of the iodine, which we just developed was exactly the same, 0.0884 moles per litre. And then I've got to divide that by the concentration of hydrogen iodide at equilibrium, and that was that great number there, 0.6232. 0.6232, and don't forget, you've got to square that number. So then we can put that into our calculator, and we're going to say 0.0884 times 0.0884. I'm going to put an equals in there, and divide that by, open the bracket, 0.6232, which was that number that we're chasing there. I'm going to square that number. I'm going to close that bracket. I'm going to hit equals. I've got 0.0201. 0.0201. 3 sig fig because my concentrations were given to sig fig in the question. And remember, there's no units because this is my KEQ for that temperature. So what we're now saying is that I've found K, it's less than 1, so that shows me that the magnitude of that number there says that the equilibrium sits to the left. It sits a little way to the left, favouring the reactant molecule, meaning that at equilibrium, I'm sitting toward this side rather than the product side. But it's not too far left. It's not an extreme left, which we sometimes see with very, very small numbers. But the magnitude of KEQ for this system indicates that the position of equilibrium sits to the left. And that's how you calculate KEQ using an icebox.